With our increasing independence on technology, 21st century's demand on inventions and development seems to be becoming boundless. From discovering drugs, working with artificial intelligence, computer and product engineering, all of this are essential to our daily lives. But with so much effort and intelligence put into these awesome works, any one of those won't be existent without one thing: mathematics. For today's topic, we will be discussing mathematics in science, technology, and engineering. Mathematics, as used in the different fields of science, provides methods in order for us to organize and structure the knowledge that we acquire. And for most part, this is true, since it is the math that provides a method, which could be applied and be used by anyone. But why is there a need for us to organize or structure our lives? Well, in math, science, and engineering, we often deal with real life and theoretical problems. For most part, in order for us to answer these questions, we have to be systematic about it, as well as provide an answer that is both reproducible and transmittable. And for us to do this, we'll just have to follow a simple common method. In 1940, George Polya put forward a four-step problem-solving process, which he then called the Polya's method. Well, this might be quite familiar with you, since this process has been used all the time in our math problems in grade school. There are four simple steps you need to follow. First, you have to understand the problem and answer what is asked. Second, you have to devise a plan. How would you attack the problem? What would be your mathematical strategy or theory? Third, after identifying the strategy, carry out the plan, substitute the given, and compute. Lastly, after getting the answer, look back and simply recheck if you got the right answer. Here, let's apply the Polya's heuristics using this simple party problem. Welcome to Math 10 exclusive party, hosted by Janella. Janella was hosting an end of the sem party for her Math 10 classmates. She invited 20 women and 15 men. For the snacks, she made 1 dozen blue cupcakes and 3 dozen red cupcakes. After the party, she noticed that she only had 5 cupcakes left. Now, how many cupcakes were eaten? Such an easy question, right? Of course, this is a piece of cake for most of you. Well, for those lucky and mathematically gifted students, feel free to go ahead and skip this part. Otherwise, SpongeBob's on the right side like me may proceed with the topic. Polya's heuristics is pretty simple. For step 1, you just have to understand the problem. You may have to restate the problem, take note of the relevant information, or cast out irrelevant information. For example, in the problem, who is the host is not relevant, as well as the gender of the guests and color of cupcakes. What is relevant are the following: number of blue and red cupcakes, number of cupcakes left, and the number of cupcakes eaten. Following that one, we'll have to identify what is unknown. In this specific problem, the total number of blue and red cupcakes is unknown, as well as the total number of cupcakes less than the cupcakes eaten. Well, after answering the two unknowns, then we can answer the number of cupcakes eaten. Now that we know what is being asked in the problem, we'll have to follow step 2, which is to devise a plan. In devising a plan, here are some tips. You may look for a pattern, practice similar problems, draw a table, diagram, or charts, or even write an equation. In some problems, we may have to work backwards in order to identify what is asked. We also have the trial and error method, which is basically guessing and checking. Lastly, we can look for sub-goal. In the party problem, we'll have to find the sub-goal first. Well, this is quite simple. We'll just have to find the actual number of cupcakes made by combining the total number of red and blue cupcakes. Also, for step 2, we can use the tip writing an equation. The party problem equation would be quantity 1 dozen plus 3 dozen minus 5 is equal to the number of cupcakes eaten. For the third step, we'll have to carry out the plan. This part of the plan is considered a logical step, which means we'll have to be extra careful. Of course, with the given equation, we'll have to attack the sub-goal first. Since 1 dozen equals 12, 1 times 12 will be equal to 12, and 3 times 12 will be equal to 36. So totally, the quantity 12 plus 36 minus 5 will be equal to the number of cupcakes eaten. That means that there are 43 cupcakes that were eaten by the visitors during the party. The fourth and last step is considered very important since many students would tend to skip this one out. But what many doesn't know, this step provides a review whether your answer is correct or incorrect. For this step, we'll have to substitute the unknown to the given. Consider the number of cupcakes left is unknown, or x, while the number of cupcakes eaten is known. If the obtained number corresponds to the given, then successful problem solving is carried out. For this problem, since 48 minus 43 equals 5, then we can say that we got the right answer. In an essence, Polia's heuristics is quite useful, since it is a backbone in solving most of scientific and mathematical problems. In the following discussions, you will be applying in one way or another these steps that we have discussed.
Counting configurations. Counting is one of the main concerns of real-world problems. To count means to determine the quantity of things or the total number of something. In counting, we have basic principles. This enables us to determine the quantity of things in the fastest possible way. These are addition principle, multiplication principle, and complementary principle. In addition principle, it states that event A has n number of ways and event B has m number of ways, then n plus m is the total outcome of events A and B. In our example, if a restaurant offers 3 vegetarian and 5 meat entries for the main course on lunch, what is the total number of meal course options of the guest? Event A is the vegetarian meal, and event B is the meat entries. Then 3 plus 5, the guests have 8 number of options for the meal. The second principle is multiplication. In this principle, we have to imagine that an event is composed of 2 consecutive steps or 2 sub-events. For instance, in picking our outfit, we have to choose a t-shirt and pair it with pants. If you have 2 t-shirts and 5 pants, then step 1 is to choose from the given 2 possible t-shirts. And step 2 is to choose from the 5 possible choices of pair of pants. Then 2 times 5, we will get 10 possible combinations of outfits. Lastly, complementary principle. It is a technique of counting where we subtract from the total number of cases. Now, let's try to apply this principle in problem solving. Problem number 1. How many ways can you arrange 10 objects in a line? Here, we see that the word arrange means the order of 10 objects in a line is important. We classify this as permutation. This has been discussed in our senior high, and permutation is where we determine the number of possible arrangement with a definite order. Our solution is factorial method. In this case, 10 factorial. 10 times 9 times 8 times 7 times 6. If you notice, there is a decrease in the value or the number of choices. The first row has 10 choices of objects to pick from. Sa second row naman, we can only have 9 possible objects from which we can choose. Bakit naging 9 na lang? Since doon sa first row natin ay we assume to pick 1 from 10 choices of objects, then mababawasan ang number of choices natin sa second row since order is important. So in the third row, we can only choose from 8 remaining possible objects, and so on until it reaches to the last part where we only have 1 possible choice of object. Hence, 10 factorial is equivalent to 3,628,800 ways of arranging the 10 distinct objects. Problem number 2. Suppose that only 4 out of 10 distinct objects are to be placed in the line. Here we will use the formula P open parentheses n, R close parentheses, or the number permutation of n from R things, where n is the number of things to choose from and we choose R of them. N is the number of things we choose from. We have 10 choices of objects and we choose R of them. We only pick 4 of them. The first row has 10 possible of choices. The second row with 9 possible of choices, the third row with 8 possible of choices, and fourth row with 7 possible choices. We stopped with fourth row with 7 possible choices because we said earlier that we can only pick 4 out of 10 distinct objects. Hence, we will get 5,040 ways of arranging things. Last example. In how many ways can a committee of 6 members be formed from a group of 12 people consisting of 5 teachers and 7 students? If we analyze closely, the question is not a permutation. Unlike the earlier example, the arrangement of things are not important. These type of question can be classified as combinations. Hence, we will use the formula C, or the number of combinations of n things taken at R is equal to the number of permutations of n from R things divided by R factorial. So the value of R is equivalent to 6 and n is equivalent to 12 because we have to form a committee with 6 members and we choose these 6 members from 12 people. The number of permutation of 12 from 6 is 12 times 11 times 10 times 9 times 8 times 7, and we divide it with 6 factorial. Then we'll have 924 combinations.
Next, we have optimization. It is significant in finding minimum and maximum values, which is practically useful for businesses to determine at which number of products can they gain maximum profit. So in understanding these optimal values, conditions must be met. A function f has an absolute maximum value on an interval I if there is some number c in I, such that f of c is greater than or equal to f of x for each x in I. And the function f has an absolute maximum value on an interval I if there is some number c in I such that f of c is less than f of x for each x in I. For example, in our figure, we see that the graph of a function attains its optimal values at the endpoints of the closed interval, where 2 and -1 is the absolute maximum and absolute minimum values of intervals -2 and 4. So in solving optimization problems, we take a look at our sample. There are 50 mango trees in a farm. Each tree produces 800 mangoes. For each additional tree planted in the farm, the output per tree drops by 10 mangoes. So the problem is how many trees should be added in order to maximize the total output of trees. First, represent the quantities by variables and identify the quantity to be maximized or minimized. We have X, additional trees planted in the farm, and O, the total output. Second, express the quantity in terms of the other variables and eliminate all but one variable in the expression. We have total output is equals to 40,000 plus 300x minus 10x squared, where the domain of O is 0 and 80 and O is continuous in its domain. Third, find the absolute extrema of the function on the indicated set. For O prime, 30 minus 20x is equals to 20 times 15 minus x. Our critical number is 15. In evaluation of the function of the critical number and on the endpoints of the interval, we have 40,000, 0, and 42,250 for the domains of the critical number. In conclusion, we need to add 15 mango trees to the farm to maximize the production of the mangoes. Next, we have the relative maximum and minimum values, which also need to meet conditions. A function of f has a relative maximum at c If f of c is greater than or equal to f of x for all x in some open interval containing c, and a function of f has a relative maximum at c if f of c is less than f of x for all x in some open interval containing c. Note that unlike absolute optimal values, relative values may not have an absolute extremum on a particular interval, such as in our figure, where if we strict values of an open interval a to e, the f of e is the relative maximum value of f, since f of e is greater than or equal to f of x for all values of x near e. So the extreme value theorem is a theorem that gives a condition in which a function is guaranteed to have an absolute extremum. It states that if a function f is continuous on a closed interval, then it has an absolute maximum and minimum values on the interval. To solve for absolute extrema in closed intervals, we have to first determine the critical numbers of the function. So we have f prime of x is equals to 3x times x minus 2. Second, we have to find the values of the function with the critical numbers and endpoints of the interval. So for f of 0 is equals to 1, f of 2 is equals to negative 3, f of negative 1 half is equals to 1/8, and f of 4 is equals to 70. So third, compare the four values from the number 2. We have 17 and negative 1 for the maximum and minimum values respectively from domains 4 and 2. Next, we have second derivative test, which is useful in knowing the rate of change at a point of the graph of the first derivative by knowing the relative maximum and minimum values. Suppose that second derivative of f is continuous near c and f prime c is equal to 0, then the second derivative of c less than 0 has a relative maximum at c, while the second derivative of c greater than 0 has a relative minimum at c.
Growth and decay. In many natural phenomena, quantities grow or decay at a rate proportional to their present size. For example, in biology, the population of bacterium grow at a rate proportional to its size. In the field of finance, the value of a savings account with continuously compounded interest increases at a rate proportional to its value. And in nuclear physics, the mass of a radioactive substance decays at a rate proportional to the mass. So generally, if yt is the value of a quantity y at time t, and if the rate of change of y with respect to t is proportional to its size yt at any time, then dy over dt is equals to ky, where k is constant. This is the rate equation. To summarize, y would be the size of the population or quantity at any time, t is time, and k is the relative growth rate or proportionality constant. Again, this formula illustrates that the value grows at a rate proportional to its quantity. This now is the general formula to calculate the quantity at any time. We must arrive at the general solution y is equals to c e raised to kt. If we were to expound, we must first multiply both sides by dt, so dt will be cancelled on the left side. After, we have dy is equal to ky times dt. We now have to separate the variables and separate y from dt. Now divide both sides by y. We'll have 1 over y dy is equal to k dt. Integrate both sides. The antiderivative of 1 over y is the natural log of y. K is a constant, so the natural derivative of dt is t. It results to ln y is equal to kt plus the constant c. Now put the equation on top of e. If e raised to ln y equal to kt plus c, then e raised to ln y is equal to e raised to kt plus c. The base of a natural log is base e, so they'll cancel. It results to y is equal to e raised to kt plus c. But you can also say that y is equal to e raised to kt times e raised to c. Since e raised to c is constant, we can just write c. This culminates to the formula y is equal to c e raised to kt. Take note, exponential growth occurs when k is greater than 0 and exponential decay happens when k is less than 0. Radioactive decay is measured in terms of half-life, which is the number of years required for the atoms in a sample to reduce in half. Again, the decay rate is proportional to the amount present. Now, suppose 10 grams of plutonium isotope were released in a nuclear accident. How long will it take for the 10 grams to decay to 1 gram if the half-life of plutonium is 24,100 years? We'll use the formula we've mentioned, with y equal to 10 when t is equal to 0. Then 10 is equal to c e raised to k times 0 and c equal to 10. We have t as 24,100 years, y equivalent to 1 half, and c equivalent to 5. After applying the formula, t must be approximately 80,059 years, and so it will take approximately 80,059 years for the 10 grams of plutonium isotope to reduce to 1. Investment and interest. If a principal amount P is invested at T at an interest rate of I for T number of years, then the accumulated value is provided by AT is equal to P times 1 plus I raised to T. Now, if the amount is compounded M times a year, then we'll derive the formula a bit, with I over M. If we talk about continuously compounded interest, the accumulated value is given by AT is equal to PE raised to IT. Applying the formula in this problem, we must find A10 if M is equal to 1. For A, following the regular procedure, the accumulated value must be 179,084.77 pesos if compounded annually. B asks the amount if compounded monthly, and the answer must be 11.58 years.
Instantaneous velocity and acceleration. First, let's define the following terms. Instantaneous means occurring or done in an instant or instantly. Velocity means rate of change of object's position with respect to a frame of reference and is a function of time. Lastly, acceleration means the rate of change of velocity. Be careful not to confuse average and instantaneous velocity and acceleration. Average velocity can be found by simply taking the displacement of the object and dividing it by the time elapsed. On the other hand, instantaneous velocity, or simply velocity, is a bit more tedious to find. This is because the formula for instantaneous velocity requires taking the derivative of the position function first with respect to time. Now, in finding average acceleration, we'll just have to simply find the change in velocity and divide it by the change in time. Simple, right? But for instantaneous acceleration, or acceleration, the acceleration of the object can be found by taking the derivative of the velocity function. Let us all visualize a problem. Suppose that you had a 13-kilometer trip from UPLB to Calamba Central Terminal riding a jeepney. If this trip lasted half an hour or 0.5 hour, how fast was the jeepney moving from UPLB to your destination, which is the Calamba Central Terminal? What was the jeepney's velocity? Of course, for average velocity, it's computed by simply taking the total distance traveled divided by the traveling time. In this case, 13 kilometers divided by 0.5 hour is equal to 26 km per hour. That's our average velocity. In this problem, the jeepney is moving 26 km per hour from UPLB to CCT. So throughout the trip, was the jeep constantly at that velocity? Well, that's quite hard to imagine. But for us to answer this question, we'll have to check the speedometer. Speedometer or speed meter is a gauge that measures and displays the instantaneous speed of a vehicle. In this case, you'll see that there is a constant change in the speed of the jeepney. That means that the jeepney was not really traveling for 26 km per hour constantly during the trip. For some time, the spike of the speedometer would have been higher or lower than 26 km per hour. For us to really determine the instantaneous velocity at a specific nick of time, then we'll have to compute using derivatives. For simplicity purposes, we'll have to assume that any object in this discussion moves in a straight line. For that, we'll have to use the equation S is equal to F times t. Suppose an object moves along a straight line. According to the equation of motion, S is equal to F times t, where S is the directed distance of the object from the origin at time t. F, in this case, is a function that describes the movement of the object, also called the position function of the object. Let us try to understand this problem. Suppose that a ball is thrown vertically upward, and given its motion equation S is equal to 80t minus 16 square feet, where S expressed in foot is the height of the ball after t seconds. Question: how high is the ball after 1 second? When will the ball hit the ground? For the first question, how high is the ball after 1 second? When t equals 1, then we'll just have to substitute 1 in the original equation. Thus, after 1 second, the ball is expected to be 64 feet above ground. For the second question, when will the ball hit the ground, we'll have to do the following. Since s equals 0 on the ground, we need to find the value of t, or time, when s equals 0. So now we have 0 is equal to 80t minus 16t squared. For the next step, we'd have to focus on the right-hand side of the equation. Since t is a common factor between 80t and 16t squared, we can regroup the following. This will give us t is equal to 0, or 80 minus 18t. Furthermore, we'd have to extract t from 80 minus 18t. That would be 80 over 18, or 40 over 9. Thus, we can safely say that after 40 over 9 seconds, or roughly 4.44 seconds, the ball will hit the ground. Hopping off to the gist of the topic, we have to use the position function f and derivatives in order for us to determine instantaneous velocity v. If s is equal to f times t is the position function of a moving object, then its simultaneous velocity v at any time t is given by this equation. Let us try and use the equation. For sample problem number 2, the position of a particle is given by the equation s is equal to t minus 4t squared, where t is measured in seconds and s in meters. The question is, find the velocity of the particle at time t. Well, the velocity of the particle is given by the equation v is equal to ds over dt, or simply take the derivative of the given function. Thus, at any time t seconds, v should equal to 1 minus 8t. This function will be our reference function when we are asked what. Here's some of the basic derivative rules which you can apply in finding the velocity. You may pause the video or copy these basic derivative rules for you to understand them better. Aside from using the function f and derivatives to determine the instantaneous velocity, we can also use both for us to determine the instantaneous acceleration a, or simply acceleration. If in initial velocity we use f prime of t, this time we'll be using f double prime t. Let's take a look at this instantaneous acceleration problem. A particle moves with position function s is equal to 3 cubed minus 4t squared minus 20t. where t is measured in seconds and s in meters. Question A. What is the particle's acceleration at time t? This time, like what we did in initial velocity, we're just determining the original function of the instantaneous acceleration. So of course, in finding for the instantaneous velocity, we have to get the first derivative of the function. This gives us v is equal to 3t squared minus 8t minus 20. Now that we know the instantaneous velocity, or simply velocity, we can simply determine the instantaneous acceleration by again getting the derivative of the instantaneous velocity. Hence, at any time t seconds, the acceleration is given by a is equal to dv over dt, which is equal to 6t minus 8. By using this equation, we can answer the question in letter B. What is the acceleration of the particle after 4 seconds? Simply with substitution, we can obtain the answer. This means that the acceleration of the particle after 4 seconds is 16 meters per second square. When is the velocity not changing? The velocity is constant if the acceleration is 0. Hence, we need to find the value of t when a is equal to 0. So, by substitution, 0 is equal to 6t minus 8. This means that extracting t from the right-hand side of the equation, we have t is equal to 4/3. Therefore, the velocity of the particle is constant after 4/3 of a second, or approximately 1.3 seconds.
The final concept in this module is the area of plane regions. The area is known as the surface of an object. Here are the different formulas that you can use to get the area of the different polygons. In retrospect, computing area of plane regions is already used during ancient civilizations to identify their land area and for the estimation of the amount of materials they need for home construction. Evidence through artifacts show that Egyptian pyramids were built by solving area problems, like this Egypt's Muscu papyrus. Greeks were also proven to have computed area of polygons by subdividing the polygon into triangles and then adding the areas of these triangles. This method is limited to polygons only. Therefore, Greeks introduced a method of exhaustion wherein polygons are inscribed and circumscribed about the figure. This method is complicated for it requires a lot of computations. In our time, we use integrals to determine area of any figure using approaches similar to the Greeks' methods. Integrals are used to determine the exact area of other plane regions with curved edges. We can compute the area of some plane regions by subdividing the region into rectangular or triangular subregions and then adding the areas of these subregions. For example, this figure, we can subdivide the region into three rectangles A, B, and C. Area A is equal to 4 times 1, and that is equal to 4. Area B is 5 times 2, and that is 10. Area C is 1 times 2, and that is 2. Add it all together, and the area of the given plane region is 16 square centimeters. This method is not appropriate for computing the area of plane regions with curved edges, like the region bounded by the parabola defined by y is equal to x squared, x-axis, and line given by x is equal to 1. To determine the area, use the Greek method of exhaustion. Rectangles are inscribed in the figure. Through the sum of the area of these rectangles, the approximation of the actual area of the region can be obtained. As you can see, as the number of rectangles increases, the sum of their areas become closer and closer to the exact area value. To limit the process, we use definite integrals to get the exact number. If f is continuous on the closed interval ab and f of x is greater than or equal to 0 in the interval, then the area of the region bounded by the graph of f, the x-axis, and the lines x is equal to a and x is equal to b is given by the integral f of x at dx evaluated from a to b. For example, find the area of the indicated region below using integral. The graph of f, if f of x is equal to x squared, the x-axis in the lines x is equal to 0 and x is equal to 1. The area of the given region is given by a is equal to the integral x squared dx evaluated from 0 to 1. Evaluating the integral yields a is equal to x cubed over 3 evaluated from 0 to 1. Simplify that and you will get 1 cubed over 3 minus 0 cubed over 3, and the area of the region is 1 over 3 square units. Area of plane regions bounded above and below by graphs of functions can also be determined by using integrals. If f and g are continuous functions on the interval ab and f of x is lesser than or equal to g of x for all values of x in the interval, then the area of the region unbounded by the graph of f, below by the graph of g, and the lines of x is equal to a and x is equal to b is given by the integral f of x minus g of x dx evaluated from a to b. For example, in the figure below enclosed by the graphs of y is equal to x squared and y is equal to square root of x, the area of the region is the integral square root of x minus x squared times dx evaluated from 0 to 1. Simplify that and you will get 2 over 3 times x raised to 3 over 2 minus 1 over 3 times x raised to 3 evaluated from 0 to 1. Simplify that further and you will get 2 over 3 times 1 raised to 3 over 2 minus 1 over 3 times 1 raised to 3. Then the area of the region is 1 over 3 square units.
In this report, we talked about the role of mathematics in solving real-world problems by showing you the fastest way of computing the possible outcome of things, determining the exponential growth and interest of a value, finding out the velocity and acceleration of moving objects, compute to optimize the volume or space of a given area, and determine areas of plane region. In addition, we explained all these concepts by showing you how to solve simple mathematical problems. Lastly, we also applied Polya's heuristic steps in understanding and solving all the given problems. That's it for our report. If you have time, you can browse the module for more examples. Thank you for listening. Have a great day.